So here we were into values and policies approximation part. So we will continue with that. So this could be one of the big picture, but there are variations to this. So what we really want to do is do some approximations of these policies. So basically we will use some neural networks. We will generate some data. So this is our data that we want to generate through various state action pairs. So this we did in last class. So basically we generate this state action pair, and with this we can fit a neural network, and that can be a predictor of an action. So this becomes our predictor. So and this is predicting the control. So here the labels are US, which is coming from the sample. So these labels are being used, and this R that we see here is a weight of the neural network parameter of neural network. Okay, so one second. So this is R is the parameter of the neural network. So this is what we mean by approximations, right? So we were looking into chess and what kind of approximations they might be doing. And so there in the classical chess they built these scoring function, which could be seen as a cost. And here they had some handcrafted features which were weighted linearly. So let us say there is a feature in the chessboard, there is a pawn structure. So this is, let's say, the structure or the pieces of your of the chessboard. So we saw in the last class that there were, in the initial research on playing chess, there were some features like material balance, like how many pieces you have, how many pieces the opponents have, the kind of pieces you have, the quality of the pieces you have, and so on. So these features are handcrafted features. Just like in the Tetris game we saw, there are some handcrafted features like 7 or 8 of them, which one can use, and then one might want to linearly make a linear combination of that. Okay, and then you can work with these features instead of the state, the actual state vectors. So for the chess they did the same thing, and even the weights were determined manually by trial and error based on experience. Some programs use supervised learning techniques. So this is what I just told you in the diagram, where we can do this, generate this data, and then we can use supervised training techniques. So for example, use grandmaster play examples. So grandmaster play could be seen as a level that you may want to emulate a grandmaster. But remember that the idea here is to predict the estimated cost, okay, and to improve on that, obviously. So what grandmaster is there is giving you an approximate cost, but with rollouts you may improve on that. So we, in a challenging RL framework, the bothersome part is how to compute the cost or how to compute the policy estimates. So we need a cheaper way to compute that. So one of the cheapest way to learn from very complex data is neural networks. Okay, this is the reason why even RL is also becoming very prominent, or any other area, computer vision, natural language processing. All this is becoming more and more, you can say, effective thanks to neural networks. So this is what we are trying to do here as well. This is why we are interested in approximations of the policy or the value. Okay, so the recent breakthrough that you see have abandoned extraction of features through human expertise. So what we see from the recent ones in the chess computer game is they have even abandoned. So we could have taken these grandmaster play examples and so on. We could have tried to emulate, but we may not even require any human expertise.
Let's welcome David. Thank you, Satinder. It's really a great pleasure to be here. So today I'm going to talk about AlphaZero, which is DeepMind's latest deep reinforcement learning architecture. It's actually achieved superhuman level in many games now, without human knowledge beyond the game rules.
The player of the black markers is the first to take a turn. Black plays a marker on the board. After the marker is placed, play moves to white. White plays a marker on the board. Players continue to take turns playing markers. The first term to know is liberties. An open intersection connected to a marker on the board is known as a liberty. Here, the marker has 4 liberties. Here, the marker has 3 liberties. Here, the marker has 2 liberties. The next term to know is unit. Markers of the same color that are connected are known as a unit. A unit will share liberties. Here, the unit of 2 markers has 6 liberties. The unit of 3 markers has 7 liberties. The next term to know is capture. When a unit's liberties are all occupied by opponent markers, the surrounded markers are captured. Here, white markers occupy all of the black markers' liberties and is captured. Here, white markers occupy all the black unit's liberties and is captured. The game ends when both players are unable to gain more control of the board or are unable to capture more of their opponent's markers. To signal the end of a game, players will pass a marker to their opponent. Here, black passes a marker to white, and white follows by passing a marker to black. After 2 consecutive passes, the game is over. Players will score the amount of open intersections they have enclosed minus any markers that were captured by their opponent. Here, black scores for 28 open intersections, minus 2 for the captured black markers, for a total of 26. White scores for 15 open intersections, minus 2 for the captured white markers, for a total of 13. Because black gets an advantage for getting to play first in the game, white gets compensated for going second. The amount should be agreed upon before the start of the game. For this game, the compensated amount is 6.5. This is added to white's final score. Black wins the game by 6.5 points. A player cannot make a play that repeats the prior position of markers on the entire board. For example, white captures a black marker here. Black is not allowed to play a marker back on the board to capture the white marker, as this would bring the game back to the prior positions. Black must play elsewhere on the board before capturing white's marker on another turn, if still possible.
So I'm now going to move on to our more recent work, which we call AlphaGo Zero. So the goal of AlphaGo Zero is to take every form of human knowledge that went into the previous version of AlphaGo and remove it from the training process, except for the rules themselves. So the idea of AlphaGo Zero is really to learn to play the game of Go tabula rasa, starting from first principles, and really understanding and discovering knowledge about the game completely for itself, without any human actually having to tell it the kind of things to do, or any human data to guide it, or anything else like that. And so the differences between AlphaGo Zero and the previous AlphaGo are essentially listed on this slide. The first and most important is that it uses no human data whatsoever. So it learns solely by self-play, by playing games against itself, and training by reinforcement learning, starting from completely random games. So in other words, we initialize our neural network to random weights, and it plays games against itself starting with those random weights, so it knows nothing about the game, and everything else is discovered from there onwards. The second difference is that AlphaGo Zero uses absolutely no handcrafted features. There's nothing in there beyond the raw board. So all it sees when it takes, the only thing that the neural network sees and receives as an input is actually a representation of the raw board. So it just has a plane saying, whether there's black stones in this position, and plane saying whether there's white stones in this position. And that's it. That's all it sees. But there are some additional differences. One of the most notable ones is that we actually unified the policy network and value network into a single neural network, again, based on a state-of-the-art residual network. And this actually helped to regularize the network and make it much more robust against the kind of overfitting which it's possible to see if you just have a value network trained by itself, for example. In addition, AlphaGo Zero actually uses a simpler search. So in previous Monte Carlo tree searches, and to an extent the previous version of AlphaGo, there was actually these randomized Monte Carlo rollouts. In other words, when you reached a leaf node, it used to do something where it would run a random game all the way to the end, and then evaluate that node based on how well that random rollout performed. And so you'd be in this situation where if random games tended to win more often, you would start to believe that was a very effective position. So actually, in AlphaGo Zero, we removed those rollouts altogether. We really wanted to have the simplest possible approach with a minimal level of knowledge. And so we removed those, and we only used the neural network to evaluate positions. And maybe one of the principles which we're after in AlphaGo Zero is this idea that by by doing less, by actually removing complexity from the algorithm, enables us to actually become more general. We want to have something which can not only be applied to the game of Go, which after all is just one domain. We want to get at the heart of what it means to really learn. We want to have something which can really learn from first principles, potentially in any domain. Of course, the game of Go is a first step, but it's a challenging first step. And if we can understand how to learn from first principles to discover knowledge and reach the highest levels of human capabilities there, maybe this is something which has more capability to transfer to other domains. So this is the goal. Less complexity, more generality.
So, for example, we can do right from scratch. In fact, sometimes you also learn the rules of the game. So the features can be extracted. I don't want to extract features via some grandmaster telling me, look, these are the interesting features, and take those. But I may want to extract it via self-play and neural networks, obviously. So, okay. So via self-play, meaning like you just keep playing.
AlphaGo Zero is the strongest Go program in the world. It outperformed all previous versions of AlphaGo. Specifically, it defeated the version of AlphaGo that won against the world champion Lee Sedol, and it beat that version of AlphaGo by 100 games to 0. So all previous versions of AlphaGo started by training from human data. And they were told, well, in this position, the human expert played this particular move, and in this other position, the human expert played here. AlphaGo Zero doesn't use any human data whatsoever. Instead, what it has to do is learn for itself completely from self-play. So the reason that playing against itself enables it to do so much better than using strong human data is that, first of all, AlphaGo always has an opponent of just the right level. So it starts off extremely naive. It starts off with completely random play. And yet, at every step of the learning process, it has an opponent, a sparring partner, if you like, that's exactly calibrated to its current level of performance. And to begin with, these players are very, very weak, but over time, they become progressively stronger and stronger and stronger. People tend to assume that machine learning is all about big data and massive amounts of computation. But actually what we saw in AlphaGo Zero is that algorithms matter much more than either compute or data availability. In fact, in AlphaGo Zero, we use more than an order of magnitude less computation than we used in previous versions of AlphaGo, and yet it was able to perform at a much higher level due to using much more principled algorithms than we had before. I think I can speak for the team by saying that we were all pleasantly surprised by just how far it went, that eventually it was able to surpass all of our expectations, and it was able to actually climb up the ratings until, after around 40 days, we found that it had actually defeated all previous versions of AlphaGo to become the strongest Go program in the world.
Again and again. So the first program to achieve this supremacy over humans is AlphaGo by AlphaZero by DeepMind, where it extracted useful features by itself. You did not even have to tell what could be the current board positions, what is the positioning of your pieces, and so on. So it learns from scratch. Okay, so that was a breakthrough. So now this happens to be the best computer chess program right now, and this is based on RL. Okay, and approximations or value function approximations, and obviously look ahead to improve on this. Okay, so overall we have a DP principles like dynamic programming that we have been learning, where they use approximate policy iterations and multi-step look ahead using Monte Carlo tree search. So this Monte Carlo tree search kind of gives you a nice organized way to search through or keep track of the useful trajectories that you want to know. So there is some detail there that someday I want to explain that there are 4 stages like selection and expansion and so on. So I will explain this MCTS in detail in some class. In one of the work we also use this for designing a better algorithm for sparse matrix reordering. Okay, so if we have time, we will discuss that as well.
One of the things that we've been talking about, sometimes explicitly, sometimes implicitly, is this notion of getting scale to actually happen. So just because I think it's important to think about scale more than in terms of abstraction, I just want to take a moment to talk about a kind of algorithmic approach to getting scaling to work that's different from just doing abstraction of the sort that we've done before, although it's going to turn out that all the things that we've done with our abstraction will actually work in this new kind of algorithmic view of scalability. That seem interesting?
Yeah, that would be really helpful.
Cool. Let's do that. All right. So here's a particular algorithm that I want to introduce. It's called Monte Carlo tree search. And there are 4 words there, and there's kind of 2 different parts. So for the beginning, I just want to concentrate on the tree search part and then tell you what I mean by the Monte Carlo part. So I want to use this picture on the right, this sort of little tree. All I'm trying to get you to think about with this tree is sort of what we've done in the past, say in an AI course, where you've got nodes representing states. There are actions that you might take that would get you to other states, and then more actions to get to other states, and kind of so on and so forth. But this particular tree has a nice little form that's kind of hidden by the edges and the nodes, and I want to sort of harp on that for a little bit. And I think it would help if you understand the algorithm that I'm trying to get through on this data structure. Okay, so the algorithm is written on the left, and it's a big loop, 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 and it works like this. There are 4 steps. The first step is selection. And I'll define what all these things mean in but a moment, but I just sort of want to go through at a high level what each one is. So the first one is selection. And selection is basically the way in which you're going to decide what actions to take from a particular state. What's going to happen is you're going to take a bunch of actions, and eventually you're going to get to some point in this sort of tree here of possible states and actions you might see where you don't know enough to know how to make a selection. Once you're at a place where you don't exactly know how you should make a selection, the idea is that you're going to expand the tree there and then do simulation to figure out what it is you ought to be doing to make selections. And the way that's going to happen is you're going to estimate from that expanded set of nodes the true value of taking actions in those states, and then in a very kind of Bellman equation sort of way, you're going to back up what you learned through your simulation, and then that will allow you to select what to do next. And you'll just keep doing that over and over and over again, making selections where you know what to do, expanding, simulating the world for a little while so that you learn what to do and then make those decisions, and so on and so forth. So does that make sense at a very high level? This is what I'm trying to accomplish here.
Yeah, I think so.
Okay.
I mean, it reminds me a lot of other kinds of tree search that I've seen in AI classes.
Like what?
A star is a kind of tree search. Game tree search is a kind of tree search. They have similar kind of pictures where you repeatedly expand nodes and get estimates of values.
Right. And in fact, I like the game search one. This is not game search because we're living in an MDP and it's just us, and so we're not playing against an opponent. But something very nice about that particular one is the way it works in that world often is you have a particular way of figuring out what action to take, or you sort of expand and do a search among a bunch of possibilities, and then eventually you run out of time. And so you have to decide what the value is of whatever leaf nodes you've gotten to. And the way you do that is use something like an evaluation function, which tells you how good we think this node is. And that's just what you've got to work on. And you use that and you back up the values, and that helps you to make a decision about what to do. And then you make a decision, then your opponent makes a decision, you end up in a state, and you do it all over again. Basically, you search out as far as you have time to search out for. When you run out of time, you use some estimate that you got from somewhere of how good the node is, and then you back that up. And that's basically what we're going to be doing here, except we have another wrinkle. And the wrinkle here is where the Monte Carlo part comes in. So the tree search is very standard. The Monte Carlo part is, well, we've got randomness, we've got stochasticity in our transition model, and so we're going to have to come up with some way to do this estimation that takes that into account, and that's where the simulation is going to come from.
Okay.
All right, so let's sort of break that up into little parts. Actually, that's a lot of words, but I think kind of walking through this picture might help. We're going to select. Well, how do we do selection in an MDP? Well, we follow a policy, right? So there's going to be some policy that we have. Let's not worry about where it comes from right now, but some policy based on experience that tells us what we ought to be doing in some state. So let's say, for the sake of argument, I'm in this particular state, and my policy tells me that I should take a particular action, and I take that action, let's say it's this one, and it ends me up in this state. Well, once we end up in this particular state, let's say the policy still tells us what to do, and it says, oh, take an action, and I'm going to take that action. I end up in yet another state, and the policy says, well, from here, you should take a particular action, so I take that action, and then I end up in this state, okay? So I have a policy. The policy tells me how to select what to do, what actions I should take, and it gets me through the tree until I get to a place where I don't know what to do. So at this point in the tree, and in fact, just so you know, the way I've drawn this tree, all the leaves of the tree are places where I don't know where to go next. I don't have a policy for it. I've got to figure out what to do. So here's what I'm going to do. I'm at this state. I don't know what to do next. I have to do something, so I'm going to do expansion, and then I'm going to do simulation. So here's how the expansion step works. From this state, I can take a bunch of actions, right? And from those actions, I can get to a bunch of states. In fact, I can just look at my transition model and I can see all the possible next states I might end up at based upon the actions that I take. And often that's what you would do. That's what you would do in a normal kind of game AI classical tree search. The problem here, of course, is that we might have many states. And so we don't want to expand out the tree that much. So instead what we're going to do is we're going to kind of do a sort of sampling step. We're going to say, well, for each of the actions that I might take, why don't I take that action and then simulate for one step what state I might end up in? And then do that for another action, and then do that for another action, and so on and so forth, until I have a few possible next state action pairs that I might see. And maybe that number is really small. Maybe it's 6, maybe it's 100. It sort of depends upon your state space. So I've done the expansion step. I figured out where I might end up next, given all the actions that I might take. So I'm not drawing this because there's not a lot of room, but each one of these edges represents some particular action I could have taken, or I did take in my imagination, and the state that I ended up in, or what the nodes represent. And so each one of these edges has some action that's associated with it. I'm just not writing it down because of space. Okay? Mm-hmm. All right. So now I've got this. So I've now expanded sort of the fringe. Here's all the things that I might do and where I might end up next. And now I have to use that to kind of decide what I actually ought to do. Now, if we were doing the normal kind of tree search, like we talked about with game search, I would just use my evaluation function. But I don't have an evaluation function. So instead, I'm going to do simulation. And what that means is I'm going to follow some other policy. We typically have a name for that. We call it the rollout policy. And just for the sake of discussion here, let's just say it's a random policy. So I'm going to say I took this particular action, I ended up in this particular state, and then I'm just going to behave randomly for a while. And then I'm going to do the same thing here. Yeah, that looks random. I'm going to do that here. And then I'm going to do that here. And then I'm going to do that here. And then I'm going to do that here. And I'm going to do that here. And I'm going to get a whole bunch of spaghetti. Now, the spaghetti actually has nice little bit, I know spaghetti's delicious. The spaghetti actually has all kinds of nice information associated with it. as I move through this path and through this trajectory by behaving randomly, say from this particular state, I actually see a bunch of rewards along the way, right? And I can just take that out as far as I need to, given my horizon, say, my discount factor. So I do this for a long time, and I collect rewards along the way. That gives me an estimate of being in this state and taking this particular action. And since I might take the same action multiple times and get to these states, I now can do a sort of average over all of these possibilities, get lots and lots of sort of estimates of this, and then that gives me an estimate of a Q value for each of the actions that I might take. So all I'm really doing is building an evaluation function by doing, well, Monte Carlo simulation from there. So I'm in the state, I took a bunch of actions, that gives me a concrete set of next states. From there, I just behave randomly for a while, I use that to gather a bunch of estimates of rewards, I add them all up, I average them appropriately, and now that gives me an estimate of the Q function. But by the way, it does more than that. Now that I have an estimate of the Q function for this state, backed up from here, I can actually back up information all the way to the top. And that updates the estimate of this particular node, and this particular node. So now that I have that, I back everything up and I can just do selection again. Now this time around, because I've changed sort of my estimates of the Q functions along the way, I might want to make a different selection. And so that actually tells us where this original policy comes from. This original policy is just an estimate of Q values that I have, where I happen to feel very comfortable about those Q values. I've visited these states many times, I've backed up a lot of information from them, so I have a decent estimate and I'm willing to do the kind of greedy policy that is implied by these Q functions.
I see. So we're taking greedy steps down the black part of the tree. When we hit a leaf, then we do the rollout policy, pi r, to get estimates of those different values. Do we now know anything new about the tree?
Yes, and in fact, if we did this, 100 bazillion times, or however many number of times we sort of wanted to, we just can say, well, I know the actions that I can take from this node, and so I feel comfortable in expanding my policy all the way down to here for this particular node as well. And if I did this again, and let's say the selection algorithm had me go here, 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 and I got back to here again, I would actually know which action I wanted to take. Say it ended up with me being here. But then once again, I've gotten to a place where I don't feel comfortable about what to do next, and I would do the expansion and the rollout again, over and over and over again. So I just keep doing this again and 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 again. And what this gives me is an ever-expanding tree where I feel more and more comfortable about my Q values and therefore more and more comfortable about a policy that I should take.
And it seems like it's getting more accurate over time.
Yeah, and in fact, if you were at each of these nodes, right, and you took those actions and you did the expansion and you did that, let's say an infinite number of times, and then you did an infinite number of rollouts over and over again, eventually you would converge to a proper Q value.
Cool, that's interesting. So this is a planning algorithm. We need to know the transition model to be able to do those rollouts.
Right. Or you have to have some way of doing the simulation. So when you say you need to know the transition model, you could mean a couple of things. You can mean I actually have the transition model and I can do calculations with it. Or you could just mean I have some way of simulating the world and I can just sample from it. So this is pretty neat, right? I think it has some neat little features to it. It allows me to kind of build up a model of the world, do a bunch of simulation and figure out what to do. But there are a couple of questions that should pop out to you, even though I kind of ran over them fairly quickly. I think the first one is, well, when do you stop? What is this actually? I mean, this is kind of an inner loop of a process, right? I'm at this state. I have an estimate of Q values that I'm comfortable enough in that I'm going to take actual actions following the policy that's implied by them. And then I'm going to keep expanding and learning more and more about it. Well, in principle, I could just do that for eternity. But at some point, you have to stop. And when do you stop? Well, you stop when you get bored.
And what do you do when you stop?
Well, once you stop, that's the next question. Well, what do I do after I stop? Well, you execute. You do a sort of one-step policy based upon what you've learned, and then you throw it all away and you do it all over again.
Wait, so you take that step in the world. You're using the policy, the whole chain that you figured out?
Well, you could, but, and in fact, sometimes, you can do actually a number of things there. But sort of the simplest version of this is, I started out with an empty tree. I'm in some particular state. I'm going to hallucinate all the things that I might do from there. As I do that, I'll be learning more and more about the world. This will allow me to do better and better exploration as I do this kind of Monte Carlo search and simulation and hallucination. And then eventually I learn enough that I know what the right thing to do is from this state, and then I do it. And then I end up wherever it is I end up in the real world. And when I'm asked to do something again, I just do it all over again.
Wow. So it does a lot of thinking each time it takes a step.
Yeah, but it's very fast thinking because, I'm just flipping coins. If I have a fast simulator and I'm able to do addition pretty quickly and maybe some, averaging, I can actually do this estimate fairly well. What's going to impact this a lot is sort of how far down I can go before I run out of computational power. Typically, that's what bored really means. Bored means, okay, I've taken 15 seconds, that's too much time. Or maybe I've taken 3 seconds, that's too much time. It's time to do the best thing that I can based upon what I know. But if I can do that every single time, if I can expand this tree pretty deeply at every time step, then I lose 50 milliseconds. But 50 milliseconds is a long time for a computer and not any time at all for human beings. And the alternative would be to actually explore the entire space and try to solve the underlying MDP. If you have a whole lot of states and a whole lot of actions, then that can take a very, very long time. So do you take 50 or 200 milliseconds every time you need to take an action and do it online, or do you take 3.5 months of supercomputing power to figure out the optimal policy and then use that? And the answer is it depends. All right, one other question I'm actually kind of surprised you didn't ask me is, what's this rollout nonsense?
Oh, I recognize that from reading about TD Gammon.
How's it the same?
The word actually comes from an understanding of how people figure out which backgammon boards are better or worse. They actually the rolling here is the rolling of the backgammon dice.
That's not at all what I was thinking.
What were you thinking?
Well, I was just thinking that we have some rollout policy, which tells us what to do when we're here. And I said, well, let's just act randomly. But I don't know why that's the right thing to do. I mean, if I end up here and I've got to do something, we're trying to get an estimate of this state and taking this particular action and ending up in this state. Why is that good or bad? And the way you're going to do it is, I'm going to say, well, I know how good it is to be here by behaving randomly from that point on. That'll give you probably an underestimate of the true value, but it would be nice if you could do something that perhaps made a little more sense. So people who've done work on MCTS have often put some effort into, well, lots of things, being clever about this expansion, keeping the right set of statistics, kind of, shoving their exploration in very smart ways. But other people have spent a little bit of effort trying to figure out, can I come up with a better policy besides behaving randomly that will help me to have a better estimate of this particular Q value? And we can talk about it. I'm going to just quickly talk about one by mentioning something that we have already talked about so far in this lesson. Do you remember the commands you came up with for Pac-Man?
Oh, it was like eat, avoid.
Right.
So it was like eat little dots, eat big dots, eat ghost, avoid.
Right. So I'm going to point out that of those 4, which I'll just call eat, and avoid, which one of those is different?
So I don't know. The first one,
Eat?
where you're eating big dots, yeah, or small dots.
Okay,
No, I guess you want me to say avoid because it's the word that's different in the list.
Avoid is different, but it's actually different in a different way. Here we said, eat a little dot, eat a big dot, eat a ghost, and avoid ghosts. Remember when I said before that, temporal abstraction becomes goal abstraction? I'm going to claim that each of these does have a goal. One is to eat little dots, one is to eat big dots, and one is to eat little goblins. But that when you execute the eat small dot, it actually terminates. At some point, you eat a small dot, and now you can move on to the next thing. At some point, you eat a large dot, and now you can move on to the next thing. At some point, you eat a goblin, and then you can move on to the next thing. But avoiding goblins, avoiding ghosts, that isn't really something that ends. You're supposed to be avoiding ghosts all the time.
I see. Well, I guess it's sort of the negation. I do understand how that's different now. So, and eating the ghost ends when you succeed. Avoiding, I want to say, ends when you fail, right?
Right.
Like I'm avoiding the ghost. I wasn't able to avoid the ghost.
Right. So in fact, these things have sort of goals. They have success conditions. They end when you succeed. Avoid is a little different. It sort of ends only when you fail. You can never succeed at avoiding ghosts. You can only fail at it in some sense. Whereas here, there's a sort of finite time in which you achieve your goal, and that's success. So it turns out that when you ask people to come up with these kinds of things, these kinds of options, they actually come up with things that look like this, lots of goals with lots of success metrics, but they also come up with things where you can sort of only fail. We actually have a word for that, and I want you to eat little dots, eat big dots, and eat big ghosts while honoring the constraint that I don't want you to be eaten by a non-scared ghost.
Okay, yeah. I mean, now from a logic standpoint, we've covered everything: success and failure. Things that are defined by success and things that are defined by failure.
Right, but the failure here, right, in exactly that way. So why did I bring all this up? I brought it up because, one, I just think it's kind of neat that people actually come up with these things. But the other thing that I think is kind of neat is that it gives us a hint. It gives us 2 hints, actually. It gives us a hint about how we might do a better job than just simply behaving randomly in our rollout policy. So here's something you might do. You might say, when I get down to here, rather than behaving randomly, and where, by the way, I sometimes will get eaten by a ghost, even though I could have easily avoided it, I'm going to try to behave randomly while still honoring whatever constraints I happen to have defined. So here, rather than trying to just walk around until something bad happens, I'm going to try to stay alive as long as possible, which is what this constraint tells me. And that's a different kind of rollout policy, but one that I claim that gives you a sort of better view of the goodness of this state. This state, action pair, is better because you can avoid violating your constraints for longer than if you are, say, in this state and take this action. And there are lots of other things that you might do. I just sort of wanted to give you a flavor of it, which is that I can use these sort of options if they are of a certain type in order to be smarter about the way I do my rollout policy. There's also another way that we can do this. I can still use options in general in this entire search up here before. Rather than taking primitive action and doing my search through the tree and my expansion, I can replace this with my actions with options as well.
Ooh.
And what's the big win there? Well, the big win there is by following the options, I'm getting deeper into the tree.
Yeah, I mean, it's the same kind of idea as in the option case that we talked about already, except now we're in trees instead of, I guess, grids.
Yes, but trees and grids, it turns out they're all the same thing. So there's lots of things you can talk about here. There's been a lot of work in this space. Some of them are available as readings for the students. I recommend thinking about them. But what's, I think, kind of nice about it is that this general notion of treating solving an MDP, not as just, I've got to solve the MDP, but as a kind of tree search problem where we take advantage of and use the randomness is something that unifies a lot of approaches that you might have.
Okay, cool.
Okay, and I think that's pretty much, I'll say one more thing about this and then I think we're done. And that's just that there are lots of ways of looking at this. You might ask yourself, is this even reinforcement learning or have we just gone back to searching? And I'm going to claim it is. I'm going to claim it's a policy search algorithm.
What's your justification for that?
Well, my justification for that is I'm basically, by building this up, I am searching over possible policies. And what I'm doing in the inner loop of searching for policies is I'm doing a kind of reinforcement learning step here when I do my backups. And in fact, the way you do the backups is you use the Bellman equation as a way of re-estimating Q values. And once I have those, I now have another policy that I'm looking at, and I just keep doing that over and over again. So I'm really searching through policy space, which is sort of what the tree expansion is. And I have a sort of inner loop every time I run out of my confidence about the policy of doing a little bit of reinforcement learning to figure out what the policy ought to be. So it's sort of policy search with an inner loop of value iteration, sort of.
And policy evaluation, Monte Carlo policy evaluation somehow.
Right, exactly. Well, that's really what it is. And the way I'm doing the policy evaluation is by doing this, doing the Monte Carlo.
So it really combines a lot of ideas that we've talked about into kind of one algorithm. Has this been successful?
It has been successful. I've actually used it in my own work. It has this really neat feature that allows you to avoid searching over lots and lots of the state space. It's actually really wonderful. It actually has a couple of properties that are worth mentioning. So let me mention those properties, and then I think properties. There's a bunch of them. One of them is that it's useful, and that in particular it's useful for large state spaces. And the reason that works, right, is that I don't have to actually look at all the states, do all of the value iteration for everything. I basically just kind of do it as I go along, and I only visit the states that I need to visit given where I happen to be in the world. There's some downsides of this, and one downside is, depending upon just how much randomness there is in your transition model, you need lots of samples in order to get a good Q-hat. But you know what? That's true anyway. If you have many states, then you're going to have to do a lot of visiting to figure out what's going on, usually. So this is the sort of, I think it's kind of intrinsic to the problem. Now, of course, if you don't have a lot of states, you still end up generating lots and lots of samples because of the way Monte Carlo works. Luckily, it's relatively inexpensive to do in most cases, at least most of the cases that we worry about. And in the end, despite all that, it has another good feature. I really like this feature. It's my favorite of its features, is that the planning time is actually independent of the number of states that you have.
Oh.
That's why it's useful for large state spaces.
I see. I mean, I guess if there's a lot of states, do we have to expand like a fixed percentage of them to know what to do?
Well, sure, you have to. That's how you're gonna generate your samples. You're gonna have to generate lots of samples that way. So yeah.
But then it's not independent of S.
Well, it is independent of S. That's one of the cool things about Monte Carlo tree search.
No, I know, but what you had said was what I asked was, so that means that as the state space gets bigger, do we have to expand? Or do we have to expand a fixed percentage of the state space?
Oh, you said percentage. I'm sorry. I didn't turn that into percentage. I'm sorry. So the answer is no, because if you did, it would depend upon the number of states.
Okay, but how could that be? How could it be that the state space gets bigger and yet we don't have to look at very much of it to know what to do?
Well, that's because you're really only you're executing through the world, and the trade-off happens in the other bullet, which is the bad thing about MCTS.
It kind of reminds me of, like, I don't know, election surveys. That's probably not the right word, but this sort of idea that you can actually get an idea of how many people are voting, no matter how big the country is, by just surveying a fixed number of people.
Right, so long as they have properties that are consistent with that are representative. And so long as you can get a representative sample of the states and the actions, then you're good.
That's really interesting.
Right. Now, of course, that's going to depend on, so to me, what's going to drive that is going to be how much randomness and entropy there is in the transition function. Right?
I see.
Because if it's completely deterministic, you don't have to do a lot of samples at all.
Yeah, that would make sense.
But there's something else that drives how expensive Monte Carlo tree search is, which is the fourth bullet that I was about to write down before you asked me this complicated question, which is that the running time
is independent of the size of the state space.
It's independent in the sense that it's exponential.
Wait, in the size of the state space?
It's exponential in the effective horizon.
So you're saying it doesn't matter how many states are in the state space, but it does matter how far into the future you need to look to make a decision.
Yes. And of course, the tree itself is growing exponentially. So you're going to need to have more and more and more of those samples to make it work. Actually, due to Kearns and his colleagues, we actually know exactly what the running time is. It is big O of the size of your action space, which makes sense because that's your branching factor. And, I need another variable here. Let's call it X, which is how many steps you're going to actually run the thing for in that loop that I did before, raised to the horizon.
Okay, so some remarks on feature extraction from data. So obviously features are denoted by phi x, and they are viewed as a function of x. And these are based on prior knowledge, right? So now the question is, if I'm looking at a feature phi x, then the possibilities of this function phi could be all possible functions in the world, right? But this is not something we can try out. We cannot try out all possible functions. For example, when you do machine learning, then you want to fit certain data. So in a machine learning problem, you also assume some prior. So if given a data, so if we want to do a basic machine learning, then this is the data I have, and I want to fit the data through certain model. Then I do come with some class of problems. We call it hypothesis class. Okay, so in the more technical term is like the hypothesis class of functions. Now, as I said, you cannot think of all possible functions in the world. You have to say what type of functions, template or the parametric, although you want to assume a parametric functions, but again you will specify which type of parametric functions you want to do. Do you want to go for parametric polynomial functions, or do you want to go for parametric neural networks? But then if you go for parametric neural network, then you tell, okay, this is these are my number of layers, these are my hidden units. So you do fix some template which we call prior. So this is what it means here. So here, if I have to fit the data, I may say, what if I do linear fit? Then these are the possible functions you are looking at. And if you will say, let me, this is your prior. So another prior could be, let us say ax square plus bx plus c, which is quadratic. So in this case, you may say this is my prior, which is quadratic. So when we are extracting features, then we will come with some class of functions that we want to fit on the policy approximation or the value function approximation. So this is what it means for prior here. Now if you want to do image recognition, then your prior is a CNN type network with convolutions and pooling layer, and followed by some classifier if you want to do classification, image recognition, or so on. So this is what we mean by prior. If you want to do NLP tasks, then you go for transformers. So transformer is a class of functions. You are not going to use CNN for NLP. Typically you don't use. So that's what we mean by prior knowledge. So this feature function that we have, depending on the problem at hand, you will choose this. There will be cases where usual neural network will be good enough to fit the data, but if it is a game where you're looking at some kind of an image and things are moving around, maybe CNN is good, because then, and in most of the games, so you will use CNN. So let us say this is chess, and let us say this is the Atari game you have, where you have this block here, and then it kind of bumps around and then comes back. So here also they use CNN. Okay, so it depends what type of problem you are going to solve. It may be a combination of CNN and some language model also. For example, in robotics, you may want to use both, because there is a sequential nature to the problem as well. Okay, so so this prior feature, you do assume some class depending on the problem at hand. Of course, we collect the data. So some features could be extracted after some preliminary calculations. So you may even want to get some features via unsupervised, like clustering. So there are some features out there. Maybe clustering will be some kind of a feature for you. So this whole group of states could be your feature y1, this feature y2, this is feature y3. So you may, as a preliminary thing, you may do the clustering first and then do some other things after that. So there may be some pre-processing or preliminary calculations you may do. So you may combine things. So okay, so if we go to the classical cases, then we may use things like Gaussian basis functions like this. So we may construct features like this. Okay, now just like polynomial, just like we have features, if we have polynomial, let's say as a simpler case, then phi L x, what are the features? If I am looking at the polynomials, then the features are the x square, x cube, xn. So this is coming from the polynomial space n. So the features that I build are like this, where I say that the state x, the square of the state x, cube of the state x is useful for me. That's how I feel. And obviously these are only features, and you do a linear combination of these. So c1 plus c2 x plus c3 x square plus dot 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 cn xn, right? And then you compare it with the expected output you have, right? So let us say level, and for many data you do this. So this is, let's say, sub 1 first sample, and then second sample, and the corresponding level, and so on, right? So these are polynomial features. Now going back to the Gaussian, then Gaussian, we build features like this. So there are also m features. So let us say this was m. So m polynomial features will look like this: 1x, x square, x, and then you do whatever. Usually we do linear combination of this, so which will look like this. Or you think that some features that we can make like this will be more useful rather than taking 1x, x square, and so on. Okay, so and these features, as you will recall, is also used in traditional machine learning when you study SVMs. So there also you have, so what we do basically there in SVMs, we typically SVMs is about a classification problem. So I mean, typically SVM is applied for classification problem, but we can also do it for regression. So basically, SVM was all about, can we build a linear classifier even when the data is not linear? That was the whole idea of SVM, because typically if a data is separable like so, so if you do a convex combination of this and a convex combination of this, so this will become a convex solve, then this is my set C1, this is my set C2, then the separation theorem guarantees that there is a hyperplane that can separate this. Then then there were issues when, and this is nice because the theory is nice here in this case, right? But when you go to cases like this, now this is not linearly separable. Then the idea was, can we still make it linearly separable? Let's say you are allowed to do some kind of data transformation. So you may map your data to a new space, and in the new space it becomes linearly separable. So that was the question that we had. Okay, so SVM did a bit more than just linear classifier, because SVM also introduced the idea of like large margin. So it's like they are like further, in a very loose sense, like they are like further as much apart as possible, and this hyperplane is nicely in between this, so that if there is a noisy data also, it is kind of robust in classifying that. So SVM was a slightly like improvement over any other perceptron based classifier. So that introduced that, but then the idea was, if my data is nonlinear, then what could be done? Then it was like, let us transform this. So this transformation that we will do will be, can be seen as features in a new space. So I apply some phi on this data, and then I go to a new space. A simplest one is to lift them like this. So the green ones go up. I use an extra dimension. So I lift this. So this 2D goes to 3D. Okay. So the green ones get lifted, and these ones, of course, it's difficult to draw this in this. So these guys are now floating higher up, just because I use some extra dimension. So this could be your one feature mapping, where the green ones coordinates became x, y, comma 1, so at one height, and the blue ones remain at 0. So the red ones coordinates still remain x, y, 0. So they remain there. So this is the feature mapping that I did. That so in this three-dimensional space, now it is linearly separable, because then a hyperplane can pass through this, where the green one is above and the red one is below. So it is linearly separable. Of course, you did a trick that you use higher dimension, right? But the point here is these features that you apply, feature mapping like Gaussian. So Gaussian kind of also does something like this. Okay, so it kind of like changes the data in like, if you see the picture, then some data get pushed up. So whatever feature mapping that you look at, if it is useful in some way, like for SVM it was useful because even for non-linearly separable data, I can apply these phi functions, map it into, even if it's a bit higher dimensional space, I can solve my problem, and I have very nice guarantees of existence of classifier and so on. So Gaussians are one of the features. So, and then you have, so these are like broad class of radial basis functions. Okay, but then you have all kind of kernels. There are people who work daily, throughout their life just on kernels in machine learning. Like they just throughout their life they are just thinking about some nice kernels for the problems or some theoretical guarantees and things like that. So for our point of view, it is now everything is set up in a very nice numerical framework where we are looking into various types of functions. It's more or less like now a maths problem, numerical problem. What type of interesting features or functions you can think of that can solve the problem at hand. You don't have to throw neural network all the time. So you can get away with some, because in some cases you need a cheaper way to do things. So polynomials are usually faster than neural networks. And some of these things are embedded devices. So they go into drones. So drone going around, they has to make some decisions on the spot. And if you apply some heavy neural networks, even the inference time will be costly. So maybe it was just a problem of simple polynomial-based approximation. So there is a trade-off between what you want to do. In some problems, you really have to use some sophisticated approximation and features. So so features is nothing but, if you have done some machine learning, then you kind of know so many ways to extract features. I told you ANN, I told you polynomial, Gaussian, radial basis. You may need RNN, transformers, all this. So all the tools that you learn from machine learning could be used here. Okay, I can briefly go through this. So we know that there are problems where we may want to do some kind of statistical estimate based on the past history. So in this case, our past history is like we are keeping track of 0 to zk information and then controls that I applied from 0 to k minus 1. So this becomes an information vector for me. Like this is something we discussed some time ago. So the state is a very abstract concept. That's what we saw, right? So state is an abstract concept. So in this case, sometimes I need to know, remember the past history. Okay. So this could be, as I said here, sometimes RNN could be useful because there is this U0, U1, U2. So it's a kind of a time series kind of data. So in this case, sometimes people do apply these things. So if a robot is moving around and there is a sequence of information that the robot has used in the past, you may feed it through RNN and see that if those sequence of steps are really important to do something in future, then you will need those sequential models like RNN transformers, which is typical in the text. Okay, so coming here, you may do any statistical approximation basically. So let us say you have, so sufficient statistics means it is enough to correctly understand the state that you are in. That's what sufficient statistics means. Okay, so whatever kind of approximation or the estimates that you are doing through Sk on Ik, that is like good enough to predict the next Ik. Okay, so we have discussed sufficient statistics before. So so in cases where you are into these, where you have kind of a history of data and so on, and then you may have to do some kind of approximations like this. Now this could be, as I said, it really depends. It's a very high level thing right now that apply some Sk on Ik, but as I said, depends on the problem what we will do here. So we will see this some specific cases here, so there is not much here. Okay, so now let us go through quickly and through. If you have done machine learning, then these type of the next set of slides will be kind of very straightforward. So it's all about approximations now, right? So we were looking for parameterized approximations functions. So this is our cost parameterized J tilde XR. R is the parameter or the weight of the neural network or linear network. So common training type is based on least square regression. So because we are into, if you remember, since we are into these cost approximations, and remember costs are typically continuous kind of values. Unlike controls, sometimes discrete controls are kind of finite. So you will build a classifier if you want to approximate the control, but typically for cost you will look at the regression problem. So the first step, because we are into supervised learning, we want to fit a parameterized model. obviously we need to gather the data, which will be our training set, and then we fit this data here, where beta s is something which is known to us. Okay, so this acts like a label. So this is what the data means. So xs is my current state, and beta s is my approximate cost calculated for the state xs. Okay, so let us say you do this in some way, that you estimated this cost and then you did it for all the states, and then you want to say, okay, I have done kind of, that's way too much, let me kind of build an approximator that can predict beta s. So obviously this is not about it will predict only for the xs that it has seen in the training sample. It should work for any state x which was similar to what it has seen in the training. So that is all the that is why we need these approximators, right? Because the state space may be very huge, and we want to kind of, for a similar state in future, we want to kind of have a good nice estimate. So obviously this is an optimization problem where we want to minimize this over r. So r is the variable unknown in the optimization problem. Now it all depends what type of optimization problem it is. Now it all depends on what type of approximation function j tilde is. Now, so we know that optimization problems come in wide variety of cases. So what could be like linear program, quadratic program, and then there are like constraint conic programming. So these are all from convex. So wherever we need optimization, I will explain you along the way. I don't plan to kind of teach it separately. Okay. So as I said, so that if whether it's linear, quadratic, conic, nonlinear, neural networks are nonlinear. So it really depends on j tilde, what it is. Okay. So right now we cannot say which type of optimization problem, which class it belongs to. Okay. So we will see like if what could be the possibilities. So cost function in general, like if you see this cost function in general, it will be non-convex. For example, straight away if you use neural network, it's non-convex. Okay, I mean typically it's usually non-convex and nonlinear and so on. So that's nothing to worry. Life is like that you have to deal with non-convex. Almost all the networks that you see, transformers, CNN, RNN, they are actually non-convex, non-linear. But still we are okay with that. We use it, we use gradient descent, minimize, and answers are typically very effective. So we are not complaining. So if there is a non-convexity, then obviously the things that we learned from optimization methods is that there are multiple local minima. So non-convex means that basically the function is like this. Convex means the function is typically like this. So if the function is like this, it's a very easy guess that there is one minima, because the function is always like a ball shaped. So ball shaped has one minima, unique minima, no problem here. But the problem in non-convex is like there are so many minima, and if you use gradient descent method, you get stuck in one of these, because gradient descent method doesn't tell you how to escape a minima. Okay, that's the whole point about this. In fact, not just gradient method, even if you apply higher order methods like Newton method, even that will not help you go to a global minima. In fact, global minima of a non-convex problem is NP hard. There is no known algorithm for a general non-convex function to arrive at global minima. So basically it's proved. So your hope of finding an algorithm to go to a global minima is in general for large class of problems not possible. But what is interesting about some of these non-convex, non-linear architectures like neural network is that although very definitely you get stuck in some local minima, but still somehow it works. The predictions kind of it gives is still interesting. So that's why people are not worried, although optimization community, the pure optimization community will complain that theoretically machine learning is not a guarantee. It goes into some one of the many local minima, things might go bad, because traditional mathematicians typically worry about existence and uniqueness. And that's some of the $1 million prizes in mathematics is for existence and uniqueness. For example, for Navier-Stokes problem. So one of the things as a mathematician you learn in many cases are theorems like existence and uniqueness. But as it turns out in machine learning, we don't have such backing of strong theoretical guarantees. This is still an open problem. Okay, why even going to one of the local minima out of so many is still okay, right? So today's class will be a little bit about optimization as well for those who are not into this. Okay, so if the architecture happens to be linear, let us go back to the objective. So here, as I said, all depends on j tilde, what type of function j tilde is. But if this j tilde happens to be linear, so what is your guess? Let us say j tilde is linear. If j tilde is linear, then this is like linear in some r minus beta s and squared. And this is a minimization in r. So there is in the objective something linear in r, but then I see a square here. So overall, this is a quadratic in r. Okay, if the objective is linear in r, since we define our loss to be like this, overall squared, then it becomes a quadratic in r. Okay, so we may make it even simpler. So all linear functions are of type ax plus b. That's it. Linear, or to be more precise, affine, because linear necessarily has to pass through origin, affine may not have to, so we put b also. So linear functions all have to be like this, ax plus b, they cannot be anything else. So it all depends on what will be your a, what will be your b, or so all affine functions has to be like this. Linear is a special case where it will be like a times x. So so basically what we are trying to say is that our optimization problem is like this: ax minus, let us say beta s is b, right? And since we have this sum of the squares, but I can change this into 2 norm, it will be similar. So it is like this, which is exactly a quadratic form, a quadratic, because if you expand this using inner product, then it will be, you can rewrite this as half x transpose ax plus some linear term. Okay, like and then ax one more with b, one more term will be there. So this is what a quadratic means, where a quadratic objective function is of the form x transpose bx plus q x plus b. All quadratic functions are like this, just like all linear functions are of the form ax plus b. So as you can see from the current derivation, if this happens to be linear, then all linears are of the form ax plus b. I think I should have done ax plus b, and then minus beta, I should have taken some beta, but b minus beta will be some c. Okay, so it doesn't matter, these are all constants. So overall it could be like ax plus b minus beta, let's say. Okay, so overall this is the quadratic term, where p will be your a, and then you can collect these px terms and so on. So this gives you a very quick introduction to quadratic programming. So basically quadratic programs are like this. This is convex when p is positive definite. Okay, so there is some requirement that p is positive definite, otherwise it won't be convex. So for linear architecture, the cost function is convex and quadratic, and as I said, with a caveat that the a is positive definite. Okay, so yeah, in this case actually it may not be, because the way it's written, because if we derive this quadratic form, it will be a transpose a, not just x transpose a. So let us do this derivation on the inner product, then you get the idea why it should be actually already convex, because it's not just a inside, it's a transpose a. So let us expand this. So this is ax plus b minus beta, right? So b minus beta, let's say, is c. So what we have is ax plus c squared. So we can write this, so 2 norm squared, we can write this as inner product. Okay, so this is like inner product with itself. So ax plus c transpose ax plus c. So this is equal to x transpose a transpose ax plus x transpose a transpose c plus c transpose ax plus c transpose c. So this term that you see here, this becomes our quadratic term, and this term that you see here, these two combine, it gives us this linear term here, and c transpose c will be like the b. So this is indeed of the form p, where p is a transpose a. Now we know that a transpose a is at least positive semi-definite, because x transpose a transpose ax is always greater than equal to 0, because x transpose a transpose ax is nothing but ax norm, and this is obviously greater than equal to 0. So it is quadratic and not strictly convex, but still it's okay. Okay, it's like semi-positive definite, but still it's the objective will be convex. So there is still a guarantee of uniqueness is there. Okay, I mean there is one local minimum. Okay, so it's quadratic convex. Now in this linear case, we claim that there is a closed form solution. So this is also coming from numerical things like linear algebra you have done before. Then this comes from there. So if the linear architecture of this form, so as I said, linear could be kind of like, so this is, this again is of the form ax. Okay, so it's like you may write it in another way, right? X transpose A or something like that. So or X transpose B. So these are all linear. Okay, if A is a column vector, then it's a special case is like this. But in general, linear functions are like this. And as a special case, when A is 1, like this is A, then it is like X transpose B, like this. Okay, so all this is fine. So we have, when our cost function is like a linear, let's say it is of the form R transpose phi x, because X transpose Y or Y transpose X is the same thing. Okay, so it doesn't matter, right? So X transpose Y or Y transpose X, you could have also written as phi transpose X, R. So this is same as phi transpose R. Okay, so if it is a linear where j tilde x r is replaced by now linear type and minus beta s n squared. So this is what is our cost, and I have already derived that it is QP, okay, and it is convex. So if it is convex, then what do you do, right? If a function is convex, then we know that to get to minima, so function is convex is like this, and it has one global minima. So local minima is global minima. So to locate the local minima, we have to locate the local minima. We use calculus, where we look at the gradient which becomes flat. So here the gradient becomes flat at this point. So basically gradient of fx must be 0 at local minima. So this is the, so basically we take the gradient of this and equate to 0. Okay, so gradient of this equate to 0. That is our next step. So and we are okay with that because it is convex. So gradient equal to 0, I'm not worried about like many solutions to gradient fx equals to 0. I know there is one solution that will satisfy this. So we take the gradient and equate to 0, And after we equate to 0, this was an optimization problem in R. So basically we are supposed to solve for R. So let us do the simplifications and see what R will be. So this is, I copied this from the previous slide. We are supposed to solve this for R. Now, how will you solve this for R? So as you can see from here, these least square problems could be solved like this. You may do this in vector form, or in this, we can keep it like this. I prefer to see this in vector form, and then it's easier to see in terms of metrics and so on. So overall, if you expand the calculation that we did before, it will look again similar to this. Okay, so if the inverse doesn't exist, so this is the inverse that we are talking about. So if you write down in terms of matrix, so this will be a this will become like a matrix, where phi s is like a vector. So you may also think this as like rank 1 updates, so q of them. So then if you add these, it will be overall a matrix. Okay, so these are rank 1, right? So these are like this. So this, oh sorry, I did it wrong way, right? It should be like this. So these are q times. So this this matrix size is the length of these feature vectors phi s, right? This feature vector phi s are, let us say, I don't know, m dimensional. So here these are m, right? So this is like m by m, m by m, m by m. So if you add these m by m, overall it's m by m matrix. I might have done a mistake in my previous vectorized calculation. Okay, but yeah, so this is m by m, and this is a inverse of this matrix, right? You could have done this as a matrix, as one matrix as well, right? So I think yeah, q times, right? Yeah. So this is like this, q times in matrix form, right? So this is like q of these, but these are like m like this, and these are like length m, but these are like q of these. So overall, it is a m by m matrix. Okay, so this you could have written this like this, phi, yeah, bar, yeah, this is what I mentioned in the previous one, phi bar, and this is phi bar transpose. So this is phi bar transpose inverse, and this is phi bar beta bar. Okay, so like this guy. So phi bar transpose, in case the inverse doesn't exist, then you can add the regularizer that I explained. So basically you add here plus lambda I in case it's not invertible. So we can, it is quite typical to add this in least square. You can also use SVD kind of approach to solve this. So basically, to solve a least square problem, we know that there are like three, you can do traditionally in 3 ways. Like normal equation form is like what we did it here. It is called normal equation, so basically, okay. Then you can use SVD, then you can use QR. So there are various ways we can kind of solve this problem. Okay, SVD is more like you have these approximation of these using SVD basically. Okay, so you kind of do an SVD of this phi matrix. So phi here is a m by p matrix. All right. So like another way to see this, and so as I said, we can always write like this, ax minus b form, where a is our phi bar, and x is our r, and b is our beta. Okay, so another view is a is our phi bar. How do I define phi bar? Is like before. So phi bar is like phi x1, phi x2, phi xp. So these themselves are m length vectors. Phi x1 is m length vector, phi x2 is m length vector, and so on. So you could have written this like this: phi r, phi bar times r minus let's say beta bar, and beta bar I can redefine as, no, that's all. So beta bar is like before, right? Beta 1, beta 2, beta s. So we can see this in terms of this, right? If you expand this, then you get this. Okay, so now when I have this form ax minus b, then the SVD approach would say approximate A by SVD. So SVD will be u sigma v transpose x minus b. Now u is like, you can take common kind of thing, like it's and you may have to do some adjustment depending on the A basically, right? Because if you do this SVD for A, if A in this case is m by p, right? So A is m by p. So the SVD that you will do, u will be of the form, if you do the truncated SVD, then it will be kind of m by p, and then sigma will be like p, there will be p singular values, and then v transpose will be p by m. Okay, so like so there will be some changes one may have to do in case like A is like less rank, right? So in this case, like m is not equal to p, obviously, so we expect that. But when doing SVD, you can take this u common and u transpose b. Okay, so assuming that we throw away the part where we work with the truncated SVD, let's say. Okay, so then it becomes a linear system, because if you want to minimize this, then it's like v transpose x equal to sigma inverse u transpose b. So again, v is orthonormal, so like so then x will be v transpose inverse sigma inverse u transpose b. Okay, so I gave you a sketch of how you do SVD. SVD could be used to also solve the least square. So we can use normal equation form, we can use SVD, and we can also do QR. Okay, so these are some of the ways. So in this case, as you can see, we can solve it in closed form. So closed form means this, right? Closed form means that you can explicitly have you can write the actual expression there, like r hat is equal to this thing, right? So this is what closed form means, right? So so if our cost function is linear, then so if our cost function was linear, j tilde xr, then we can see that we can explicitly solve for the parameter. However, if it is not linear, then as we know, it will be this case, and we may use some gradient descent. Now in the neural network based approximations, a vector x goes in as input, and then it may go through some feature extraction, problem specific feature extraction, and then it gets y, and this y goes through this linear combination of the y. So a yx plus b. A in this case will be the weights of the network, and then we add a bias term b, And then we do a nonlinear activation by some activation functions like phi 1, phi 2, phi m. No, I mean, no, not that. Like yeah, the output is phi 1, phi 2, phi m. But let's say it went via some sigmoid or ReLU, whatever is there, and the outcome that we get is like the features phi 1 to phi m. And these features, again, we can do some linear weighting, right? So finally we say, okay, these are our features that is extracted by the neural network. Now do a linear weighting. So this will be R transpose phi. And so this is our approximate cost, which is which we may kind of solve for R. Okay, but then in this case, what we are thinking is, like we may think of this as like two-step process, where there is a neural network to extract the features. Neural network itself have parameters, and which needs to be kind of learned. And the second stage is where, assuming that these parameters are found, now we have a parameter R which only acts linearly on these features phi. So we see this as two-step process, right? We have a neural network with its own parameters like V, and then we have another parameter R. You may see this as two-step process, but you may see this as one-step process also. You may take this R, X, all the R and the V as whole set of parameters, and pass the gradients throughout, and update the weights of the neural network as well. Okay, so in the typical machine learning framework that you do, okay, so it is okay to treat this as one big parametric network, rather than saying the first half is feature extraction with parameter V, and the second half is the cost approximation parameter R. It is okay to kind of train this as a full throughout, because there is a level beta here. So this cost will be R transpose phi x b minus beta. So it's not just R that you are trying to learn, you also the V that you are trying to learn. So you may do the gradient descent and do gradient flow throughout these network, right? So whereas in this case the way it is done is like a two-step process, right? So there is a feature and then there is a linear combination of feature. Okay, so in this this is how the training of the neural network will happen, which we now combine in this optimization problem. It is a minimization over A, B, R. So A was the neural network parameter, B was the bias, which is also a parameter of a network, and R was for the last linear combination, right? And so all this you combine, and this is like through a complete training process, right? But from our understanding, it's like there is a feature extraction, and then there is a linear, there is a parametric linear function of the features, right? But through and through, this is just a highly nonlinear. If you see in terms of all the, in R it is linear, but in A, B, R combined, it's highly nonlinear and non-convex. So this problem is generally non-convex, multiple local minima. We can augment the regularizer, so that's very common to add regularizer. So you may add some additional L2 regularizer, L1 regularizer. At least for neural network training, it helps in preventing overfitting. Okay, so these are the things that we do. So some remarks. So in dynamic programming or in RL, we mainly approximate, we do only, like typically we approximate two types, cost functions or policies, okay? So what we have seen so far is we have parameterized the cost, J tilde, XR, we parameterized, okay? But we could have done this for the policy as well. So in RL literature, so when neural networks are used to approximate, then they use the word network. As such, you just say approximate function or something like that. But then you use neural network in these approximations. If you use neural network to approximate the cost or the value, then we call it value network. And if you approximate the policy mu, then it's policy network. Now, alternative terms that are used are like a critic network and an actor network. Okay, so these are another like other popular terms used here. So actor could be like a critic which keeps taking actions and things like that, and there is a critic which is the value cost function that tells you like it acts like a critic. Okay, so you did certain actions, things like that, and then let me tell you what was your final cost. So it is possible to combine both, obviously. So what we have seen is only approximation for the value network, but we can do both. We have approximation for the policy as well as for the cost in the same algorithm. We can mix both. So it is useful to use Q factors. Now, in a fitted value approximations, what we do is the parameters Rk that we have, these are determined sequentially. So we have this finite horizon with stages like k. So now we can think of these as at the kth step, what is the parameter? At the k plus 1 step, what is the parameter that I learned, and so on. So in the DP algorithm, usually we know we go from like terminal to the so we may build a cost function approximation for the terminal stage and then proceed backwards and so on. So we may have this sequence of parameters to learn, like n-1, n-2, and then the R0 is like the at the terminal. Terminal is like the beginning, right? So states space for each stage k is sample, generating a large number of states xks. So S can vary depending on how many samples you want to collect. Let us say Q, then we will collect Q of these samples at stage K, right? So, and then we can learn these parameters using a least square fit. This is also applicable to the infinite horizon. And so let us see. This is the equation to do this sequentially. So this is our parameter R. So this is the parameter R that learns to predict the cost at stage K. So this is the parameter Rk that learns to predict the cost at K. So what we are trying to say is that our parametric cost approximation is for each stage now. So there is, so at J1 there is a approximation function there is no universal cost in our hand. What we are saying is like at stage K I have a parametric cost function with parameter R1. At stage 2 I have a parametric cost approximation R2 and so on. Okay, it is not like a shared parametric space. Each stage have its own parameters and approximation function. Okay, it may work in some cases that you have the same approximation function which depending on the x it still gives you some cost estimate. But this is one possibility where we see different approximation for each k. So so this is how we kind of approximate these Rk, where at stage k I have the labels which are, these are my labels. Okay, and we know this because we have found k plus 1 because we are going backwards. So we have found k plus 1. So for k plus 1 the j tilde is learned. So this cost function knows how to predict for k plus 1 onward, because this fk when applied to xk is working on the state k plus 1. Okay, so because the outcome of these will be k plus 1. So this cost function at k plus 1 is known. Okay, and then this local cost at the current xk we add. So this becomes like our label. Okay, so this red thing is our label, and these are our kind of the data. Okay, the features or whatever, right? So data typically includes label also sometimes. So so this is what we are doing. We are building a function approximator. So this could be, again, as I said, neural network, right, at each stage with parameter R. So this is kind of simple, right? It's just that we are building cost approximator at each stage k. So this is known, as I said, what I explained is the same thing here. We can say that this whole thing that is known is some beta s. So then it is overall, it is this optimization problem that we are trying to solve, where our cost is of this form. And we can keep doing this. The algorithm initiates at stage n-1. We keep going backward. It concludes at r equals to 0, at k equals to 0. And yeah, these are the same arguments. Like if j tilde, the cost approximator at each stage is linear, then you do have a closed form approximation. So we already discussed, so no need to waste time on this. So we can, so remarks on fitted thing. So how do you collect samples? Well, you can collect samples via various means. For example, you can do Monte Carlo simulations. So Monte Carlo simulation is basically just pick some of these samples randomly. That's what Monte Carlo means. Monte Carlo is about just sampling randomly, uniformly, or whatever distribution you favor. You sample these states randomly, and then but the sample states that you use in your training data must be representative. So doing very like, although it is random, but still, if it is not representative, then kind of you will take a long time to learn, because the useful samples may be very limited in the training data. So maybe you make sure that these are the states which are close to nearly optimal policy. Now you may say, how do I know whether it's nearly optimal already, because I'm still training, right? So you may use some heuristic way, like to kind of remain close to the policy, or like not deviate too much from the existing policy. So we'll see a bit more of this, like how this sampling could be done in a better way. Frequencies with which various states appear in the sample should be roughly proportional to the probability. Yeah, so again, it's like if there is a state which occurs more frequently under an optimal policy, again, as I said, we don't know optimal policy, right? So this is like, yeah, but ideally, the states that we sample in training data, if the state appears frequently, then it should be more of these in the training data. That way, the frequency should also kind of match. So there are difficulties with the fitted value iteration when n is very long. Obviously, when n is long, then we know that there will be computational problems, because in fitted value, what we are saying is that each approximation is separate. The stage k approximator is different from, because it has its own parameter. So it's different from, like structurally maybe it's not different. They may use like the same neural network, but it has its own parameter, and another stage it has its own. So it keeps own copy of parameters. Now we have seen there is that in our cost there is a beta term involved, like here. So we define beta to be like this, right? So one thing is like, so this acts like a level for us in the training. So the first, so one of the things to ask is like how well we can compute these levels, right? Because there is an expectation involved here. So when expectations are involved, things are tricky, because it's a minimum over expectations. So as if it looks like you collect a sample, and then you, on those samples, you take the average, and it's a minimum of the average. So there, in some sense, this is still an estimate, because we will collect some samples and their average and the minimum over that. And then if you would have collected some other samples, the average would have been different, and then minimum for that, right? So because of this expectation term, it is a tricky term. So we will see what to do with that. So to conclude, there is a significant challenge with the training data when computing the sample's beta case, which involves minimizing an expected value. Because it's an expected value, just for that, at the case stage, you are supposed to minimize the expectation of something, but to have an estimate of the expected, because you don't know the distribution anyway. So it's not like someone told you this is Bernoulli, this is binomial. So you know the expectation of these. It's not given to you. These are from these are just collected, and then you have to go for sample mean. So sample mean needs sample. So that is time consuming. You have to collect lot of samples to be sure that this is a good estimate of the expectation term. An alternative fitted value iteration will use Q factors that involves a simpler minimization. So this is where we will go next time, where we will reverse the minimization and expectation operation. So we will see, like, can we, if we flip, then whether this will make our lives easier. Okay, so we plan to flip this mean and expectation here in the beta. Okay, so this is something we will do in the next class.